Hello, I'm going to show you how to use the R companion package's compmeansC function to test hypotheses about means using analysis of variance. I'm assuming you've already downloaded RStudio, and have installed the RCPA3 package. If you haven't done those things already, you'll want to complete your setup before trying to use functions from the package. I'm also assuming you have a basic understanding of how to work in the R environment. If you don't know what functions and objects are, you should review Chapter 1 before practicing the methods shown in this video. The compmeansC function is one of the most powerful functions in the RCPA3 package, and we use it a lot in the book. The required arguments are fairly simple, but there are a lot of optional arguments and plot-related arguments which allow you to do a lot with the compmeansC function. In this video, I'm going to focus on the compmeansC function's optional arguments for analysis of variance. I cover other uses of compmeansC, like making basic comparisons, generating plots, and controlled comparisons in separate videos. The compmeansC function has two required arguments. dv is set equal to the dependent variable, and iv is set equal to the independent variable. The compmeansC function supports a standard set of optional arguments. If the independent variable has more than two categories, you can test for differences among multiple means by setting the function's ANOVA argument to true. The function will then return an ANOVA table along with a mean comparison table. If you're making a controlled comparison by setting the z argument equal to the control variable, you can set the function's ANOVA argument to true for two-factor ANOVA. Before you use compmeansC to test hypotheses about means, make sure you're using the right function for the problem you're working on. If the independent variable has just two categories, use the testmeansC function to test the difference between two means. If the independent variable has more than two categories, but the dependent variable is nominal or ordinal level, use the crosstabc function with options for conducting chi-square tests. To learn how to use the compmeansC function to test hypotheses about means, let's work through some examples. Okay, so to run single-factor ANOVA with the compmeansC function, recommendation would be to start with a compmeansC function call and look at a mean comparison table first, and then add the ANOVA argument to it. So ANOVA is used to compare means among multiple groups. So I'm going to have a dependent variable, and we'll have an independent variable. So I'm going to pick something from the states data set, some interval level variable, and compare it by region. So we'll do advanced degrees, or well, let's do college degrees or more by region. So first run is a mean comparison table. I'm sure we'll see the plot as well, showing the mean values. Get a sense of what they look like, and then I'm going to add ANOVA to it. The ANOVA argument is an option. By default it's false, and if we want to run it, we set it equal to true. And then in the results, we have our mean comparison table, descriptive statistics, and then the analysis of variance. So we can see from the results that the statistic is 6.91, and the probability is lower than 0.05. To do two-factor ANOVA with the compmeansC function, recommend looking at the controlled mean comparison table first, getting a sense of the descriptive statistics, and then adding the ANOVA argument to it to do your two-factor ANOVA. So I have a compmeansC function call here. I'm going to compare a feeling thermometer variable by gender, controlling for party identification. So to complete this, I'm going to add on a feeling thermometer variable, and I thought it might be interesting to look at feeling thermometer toward Vice President Kamala Harris after the election. And I want to add on a weights argument since we're using the NES data set. So here's our initial compmeansC function call, and I'm going to run it, and then we will look at the results. So the table is a little hard to read because it's breaking lines. I'm going to do a couple tricks. I already know I was going to do this, so I've already written here in the comments. So what I'm going to do is add an Ivy Labs argument to shorten the independent variable labels from what's shown to males and females. Also going to shorten the value labels for the control variable to Democrats, Independents, and Republicans. And also use this compact equals true argument. What that does is, you can see on the table, if you look closely here, for each value of the control variable, it's reporting the mean, the n, and the standard deviation. And if you do the mean, the n, and the standard deviation for 3 different values of the control variable, that's at least 9 columns. So I want to shorten that. Compact equals true will have us just report the mean. So let's run this, see what we're looking at, and then we'll add ANOVA to it. Okay, so pretty nice simple plot here. We have the mean feeling thermometer toward Kamala Harris, comparing males and females, controlling for party ID, Democrats, Independents, and Republicans, and we can see a plot of that relationship in the plot window. To do a two-factor ANOVA on this relationship, we can use the ANOVA argument for compmeansC, and by default it's false, but we will set it equal to true, and we'll run this. So as you can see, when we've run the ANOVA equals true, it's added the analysis of variance table. Doing a two-factor ANOVA, the table is our ANOVA table with type 2 tests. The independent variable was gender. It has an F statistic of 10.38, which has a p-value with these degrees of freedom of less than 0.05. And for the Z variable, it also looks at the analysis of variance for the control variable party ID. It has an F statistic of a whopping 2,139, and it has a p-value of less than 0.05. That whopping F statistic for the Z control variable party ID isn't very surprising. It's just telling us that the relationship between party identification and feeling thermometer toward the Democratic Vice President of the United States varies significantly with party identification. No surprise, you see it clearly in the plot, and the two-factor ANOVA table backs that up.